All right, so lucky for you guys, I'm gonna back up a little bit. So, um, so we're talking about perpendicular spaces, right? So we're talking about, given a space L, we're talking about the space that's orthogonal to it. Or given a plane, we're talking about the line that's orthogonal to it. Okay? And so then we'll call that space W perp. Okay, the orthogonal complement. So then, looking at the activity, we set up W1 and W2, right? And so then we were asking part A, what does this equation mean? And this equation means, like, just do out that dot product with 1, 0, negative 2, and these guys, and you get x1 minus 2x3 is 0. And we looked at what this equation means, and it means that, remember that W2 was the vector 1, 1, negative 1. So that means this equation must be true. And then if both equations are true at the same time, that's a system of equations like we talked about at the beginning of our class, which means we've got a situation like, this is wrong. Nobody caught that. Missed a gold star. x1, x2, x3. So then B is the matrix such that times x1, x2, x3, you get 0, 0. B is this matrix. Basically, it's the vectors as columns, but then transpose. So then we said, well, anything that's linear combination of W1 and W2 will just be like distribute it. Then you get zeros there, so it's 0. So then any linear combination of W1 and W2 will also be orthogonal to X. And then we got to here, and we wanted to find, we wanted to find a basis for W perpendicular. Okay? So then I'm left with like this equation here. What sort of thing am I doing here? Yeah. The null space, right? How do we do the null space? How do we find the null space again? Yeah. Yes. And we're only one move away from being reduced to echelon form here. So if I annihilate the 1 by doing negative row 1 added to row 2, you go there, there, negative that added to that is there. And so then we're left with this sort of situation. And so, and then you kind of would, because you've got the 0, 0s there, you could augment the 0, 0 there, right? And then what does this mean? This means that, well, I can do it a couple ways. Why don't I do it with my Kyle numbers, okay? So color, I've got a free column, so put the 1 over there, and then the negative 2 goes over here, that's positive 2. The 1 goes over here, becomes negative 1. And so basically, this is the span of the vector 2, negative 1, 1. Okay? So then W perp, that's W perp. Okay? It's one-dimensional. Make sense? All right. So, what do you guys think? What would be W perp perp? Your thought? What's that? W. Yeah? Because if I tried to do that all over again, I'd get back to W. Okay, I might get a slightly different basis, but it'd be the same space. All right. Now let's look at an example. So here, we've got an example where L is the line defined by 1, negative 2, 3 in R3. And we want to describe the orthogonal complement. And so then the orthogonal complement is going to be all the x1, x2, x3 vectors such that this dot product is 0, which means like this equation is true. And so then if you write that as basically like solve for x1, if I take that equation and solve for x1, then x1 equals 2x2 minus 3x3, right? So if I put that there, and then x2 and x3 are free, then you can write that as like x2 times that vector plus x3 times that vector, right? Where the 2 and the 1 come from here, and the negative 3 and the 1 come from here. And then that means the orthogonal complement L perp is a plane, and I found a basis for the subspace, this one and this one, right? Questions about that? So it's just finding a basis for the null space. Okay? Suppose W is the two-dimensional subspace of R5 with this basis. Okay? So then, like it's got this vector and that vector. So then anything in the perpendicular space will have dot product of those vectors be 0, which gives me these two equations. These equations equal to 0. In other words, like Bx equals 0, where B is the vectors put in as rows, right? And then here's the Gauss-Jordan elimination. And so then the solution, like if I look at that, let's come up with the Kyle numbers. So help me out here. How does this work? How do we do this again? I know it's the last Friday of the semester. We're looking low energy. So how do we do this?
Since there's 3 free columns, when you put like 1, 1, 2, 0.
Yeah. So I'll do that one, and I'll do that one, and I'll do this one. So 3 free columns means 3 of those guys. And so then this guy goes to that pivot, so -2 there. And then this guy goes to that pivot, so 0 there. And then here, I'm dealing with this free column. So -1 goes to that pivot, 1. And 1 goes to that pivot, -1. And then here, this guy, 2, goes to that pivot, so -2. And then -1 goes to that pivot, so +1. Now double check. For each of these, like -2 times this, plus 1 times that, plus 0 times all those, does that equal 0, 0? All right, and look at just like here. So like this guy minus this guy plus this guy, because of that. This guy plus this guy minus this guy, what does that be? Is that the 0 vector? This guy, so this guy, minus this guy, plus this guy. 0 vector? Yes. All right, and then what if I had -2 times this, plus 1 times this, plus 1 times that? What will that give me? 0 vector. We're good. So then, those 3 vectors are right here. So this guy goes to there. This guy goes to there. This guy goes to there. And that means my perpendicular space is 3-dimensional with that basis right there. Okay? Okay. So W perp is a 3-dimensional space, subspace of a 5-dimensional space. All right, so the transpose of a matrix is when you swap rows and columns. Make all your rows your columns and your columns your rows. That's the transpose. Okay? So if A is this matrix, A transpose is this matrix. Okay? This is something we kind of talked about before, but we're saying it for real now. Okay? So here's a simple one. There's B. Write the matrix B transpose. Okay? So our rows become our columns and our columns become our rows. So here I've got these two columns here, they now become these rows here. Okay? Suppose that V1 is that, V2 is that, and W is that. Find the dot products. V1 dot product with W and V2 dot product with W.
Wait, can you go back up to the transpose?
Yeah.
Okay, cool.
Yep.
Just wanted to make sure.
Yeah. Okay. So now, what did we get? Are we still working? Do we need time? I see people still working. Okay, what did you get for the dot product of V1 and W? -10. Someone else, what did you get for the dot product of V2 and W? 6. Okay. Now write the matrix A as columns V1, V2, and the transpose A transpose. And then do A transpose W. Okay. So, what do you notice? They are the same. So A transpose times W is the same as doing the dot product with those vectors in W. Okay? So it's a good way of organizing, like when you're doing a bunch of dot products. Okay? So say that X is a vector. There's an orthogonal of V1 and V2. What does that say about this and this? What does that say about this? Okay, we know they're the same, but if it's orthogonal, what does that tell us about those guys? 0. And so then A transpose X would be the 0 vector. Right? Well, use the matrix A transpose to give a parametric description of all the vectors X that are orthogonal to V1 and V2. Feel free to work together. Check your answers with people around you. Okay. So this is intentionally created with some nice numbers. So we can divide by 2, and then annihilate the 1 there, and then we're already done. And so then our Kyle numbers put a 1 there, which means -3 there, and +1 there. And so the null space of A transpose is that. The null space of A transpose is basically like W, whatever space this is. What do we call the space V1 and V2? We never called it anything. So, all right. So, if X is a vector in null A transpose, Y must be orthogonal to both V1 and V2. Let's talk through this one. Okay? So if X is in the null space of A transpose, then what does that mean? That means A transpose X equals 0. Right? Which means like vectors V1 and V2 times X equals 0, which means that V1 dot X equals 0 and V2 dot X equals 0. So that means X is orthogonal. So that means X is orthogonal to V1 and V2. Okay. Remember the column space of A. The column space of A is the set of linear combinations of the columns of A. Therefore, any vector in the column space of A can be written as C1v1 plus C2v2. If X is a vector null of A transpose, explain why X is orthogonal to every vector in column A. What do you guys think? Is this something you feel like you can answer, like share with someone near you, or do you want my help here?
Your help.
Thank you, Mackenzie. Thank you. Somebody woke up. You guys ever read the Narnia Chronicles? Like, have you guys? Some of you have read the Narnia Chronicles. The lesser read of one of the books is like the Silver Chair. So in the Silver Chair, kind of takes place. There's these two characters going into the land of giants, stuff like this. There's this character named Puddleglum, and Puddleglum is just like the biggest pessimist. He's just so annoying. But then there's this time towards the end. I'm going to spoil it for you because whatever. So there's this time towards the end where the witch has them enchanted, but Puddleglum is the only person who has the clear enough head to like put out the enchanted fire, and everyone's like, "Oh, so Mackenzie, you are a Puddleglum today. Great job." All right, so if X is orthogonal to the columns of A, then basically from above, right? Like, i.e., X, like V1 equals 0, x v2 equals 0, etc., then x dot product with like a1 v1 plus a2 v2 is going to equal a x dot v1 plus x a2 x dot v2, which is equal to 0 plus 0 plus just 0. So anything that's in, if x is orthogonal to the columns of A, then anything in the column space will be a linear combination of the columns of A. And so x dot product with any of that linear combination, well, dot product distributes. So you just distribute it, and you get 0 plus 0, so it's 0. Okay? So x is orthogonal to everything in column space of A because it's orthogonal to the columns of A. Okay? So let's say it as a proposition for doing the true-false questions. So if A is a matrix whose columns are v1 through vn, then A transpose x is all these dot products. Okay, any questions about that? All right. So then, suppose W is a subspace of R4, and it's with this basis, this one and this one. And we want to describe the orthogonal complement W perp. So if A is a matrix with columns W1 and W2, and if X is in W perp, then basically we know this must be true, which is basically like, we know that's true. And so then describing the vectors X that are orthogonal to W1 and W2 is equivalent to the more familiar task of finding solutions of this, of A transpose X equals 0. Okay? The power of linear algebra is when I can take a new problem and turn it into an old problem. Right? So, and like the theme of this class is all the things you can solve using reduced echelon form. Right? So, so to find, so to do so, find reduced echelon form of A transpose, and basically we're going to cut to the chase, so you use a computer to do that. Then you use your Kyle numbers, and you get these guys, and so then, so such a vector X is going to be orthogonal to W1 and W2. Okay? So then V1 and V2, these guys, so call this guy V1, call this guy V2, then they form the basis of W perp. Okay? So then, here's our proposition. For any matrix A, the orthogonal complement of the column space of A is the null space of A transpose. Okay? Now this is really fun. The fact that we're using the perp sign as this and the transpose sign as that. Okay? So, column space perp is equal to null of A transpose. Okay? It's like you're taking your T and flipping it upside down. Isn't that fun? All right. So again, like what does this mean? So remember that column space is the linear combinations of the columns of A. And the perpendicular part of that is like what's perpendicular to it. And then what's perpendicular to it is the null space of A transpose. And so then this is how null space and column space are related. Okay? Perhaps a great thing to write down for the formula sheet for the final. Okay? All right, 624 is online. Grab a computer or grab someone next to you who has a computer. Let's do it. Everyone got part A working?
Oh. Here we go.
Oh, you're doing some other So for part B, we want to show A, and you can do A transpose like that. What do you notice about the determinant of C and C transpose? They are the same. So the algorithm for finding the determinant works the same as if you work along a column, or work along a row, or work along a column.
Go back and play.
Yeah. A is 2 by 3. So for D.2, A is a 2 by 3 and C is a 3 by 3, right? And so A times C makes sense because the 3 and the 3 match up, right? But if I try to do, A transpose, that's a 3 by 2. C transpose is still a 3 by 3. So if I try to do A transpose times C transpose, what happens? I'm trying to multiply matrices that are the wrong sizes. Okay? And if I try to do that, if I try to do this in Sage, it'll give me an error. But can I do C transpose A transpose? Yes, because if I do this one first, then that 3 and that 3 match up. So notice how AC transpose and C transpose times A transpose are the same matrix. So transpose is another reversing operation. If I move it from the outside to the inside, I need to reverse the order of multiplication. Okay? So just like inverse, it reverses the orders. And then the identity transpose is just the identity, right? Okay. Now this last one, the last one you can't really do with Sage. So if D is invertible, then what do we know? What does it mean to be invertible? It's a silly question almost. It has an inverse, right? So then there exists a matrix D inverse such that D times D inverse equals the identity, and D inverse times D equals the identity. Okay? What if I take both those equations? And what if I take the transpose of both equations? Then, oh, come on. You got this. Come on. Just. Then, D inverse, take transpose of both sides, equals identity transpose. And D inverse D transpose equals identity transpose. Right? Because if two matrices are equal, the transposes will be equal. Doesn't that make sense? Okay. How can I, if I move the transpose through, what happens? So then, if I move the transpose inside, then I swap the order. So D inverse transpose times D transpose equals, and the identity transpose is itself. And then I swap the order on this one, so then D transpose times D inverse transpose equals identity. D transpose times this guy is the identity. What does that make this guy? I'm asking the question, is D transpose invertible? What does it mean to be invertible? There exists an inverse, right? Well, here's D transpose, and I multiply it by this guy, I get the identity, and I multiply on the other side by this guy, I get the identity. So what does that make? What does that make this guy? The inverse of D transpose. How do I write the inverse of D transpose? So that means the inverse of D transpose would be D transpose inverse, right? D transpose inverse is the inverse of D transpose. And then the thing that is this guy is this thing. The one that I multiply it by to get identity. And this guy is D inverse transpose. That was a proof. I don't get to do that often in this class. But all right. So D transpose inverse equals D inverse transpose. Okay? All right, this was, I did this, I did this, I did this, I did this, did this, did that. Okay. Suppose W is a 5-dimensional subspace of R9, and A is a matrix whose columns form a basis of W. That is, column space of A equals W. Answer these questions. Feel free to work together. Prepare your answers. You have no idea. Talk to someone near you. All right, let's start talking about this. What is the shape of A? 9 by 5. Okay, it's going to have 9 rows, 5 columns, right? Because it's made up of vectors in here. And we put them in as columns. So it's going to have 9 rows, 5 columns. Okay, and what's the rank? 5. Okay, and what is the shape of A transpose? 5 by 9. What is the rank of A transpose? Also 5, because basically, like, reduced rational form is going to be the same number of pivots. Then, what is the dimension of the null space of A transpose? 4, right? Because the dimension of the null space of A transpose is the number of free columns, right? Rank is the number of pivots. This next answer is the number of free columns, that's 4, basically like 9 minus 5, which means that the dimension of W perp is 4. And how are they related? 5 plus 4 equals 9. Right? The dimensions of W and W perp add up to 9.
So the dimensions of W is 5, right?
No, W is 5-dimensional. So W perp is 4-dimensional. Mm-hmm. All right. Now, the next part. Go to the online textbook. module condition represent coordinate vector has user basis. Oh, I just call basis. Haha, all right. Yeah.
Maybe I can do that without messing this up.
One, zero, two, nine.
Like we get, do something that's basically, so I basically get the same answers. 1, 0, 0, 0 without messing with some answers. I'm guessing not, but.
You can do that, but you did that transpose at the end?
Yeah.
Good for you. All right. So you're getting a different answer than me?
Okay.
We're getting the same answer. What do you need? Oh, right, yeah. Yeah, here, no, do this. W1, 2 equals oh.
Yeah. Well, I'm gonna do that.
Okay. Okay. Um, so is everyone able to verify? Everyone get to those vectors and verify the dot products were 0? Okay. I want to do a little bit of a high level talk through of some stuff that we didn't have time to go through. And then we'll take a 5-minute break. Okay? So, the next section, we would have talked about how to make a basis orthogonal. Okay? So, for instance, if you have these vectors like here, this is what your prevectivity would have been. Like this one, dot product with that one, you get 0, 0, or you get 0, right? And so then orthogonal sets are like when you've got, say, 3 vectors. And these guys, their dot product is 0, because you'd have 1 minus 1 plus 0 is 0. And these guys are orthogonal, because you'd have 1 plus 1 minus 2 is 0. And these guys are orthogonal, because you'd have 1 minus 1 plus 0 is 0. So all 3 are orthogonal to each other. Okay? Which means they're somewhat like our normal like I, J, and K, or E1, E2, E3 sort of thing. Okay? So not only is there a basis, but they're closer to like what we think of as like our standard basis. Okay? And so these guys are an example of 3 vectors that are all pairwise orthogonal, and they're in R4. Okay? Now, suppose that a vector B is a linear combination of orthogonal vectors. Okay? Then, if you looked at like, if you took B and took this equation and took its dot product with W1, okay? Just trust me about this while we're doing this. Dot product with W1, then that means like the dot product of W1 distributes. So then they're all orthogonal. So this one is 0, that one's 0, that one's 0, 0, 0, 0. The only one that's not 0 is W1 with itself. And so you get this. And then you get the scalar. C1 is equal to that. Right? Now before, when I wanted to solve for these guys, I'd have to do reduced to echelon form. But if my vectors are orthogonal, there's a faster way. The faster way to find each coefficient is doing like dot product divided by dot product. What does this remind you of here? From Calc 3? What does this remind you of from Calc 3?
Oh, it's one of the vectors. The whole vector? I don't remember.
It's part of the projection formula.
I know.
So if I were to take B and project it onto this vector, the answer would be C1 times W1. Okay? And so then you can write B as all this, like B is just projection of B onto W1 plus projection of B onto W2 plus projection of B onto Wn, so on and so forth. Okay? So we're not just doing this to torture students. There's a reason for this. So then orthogonal vectors are linearly independent, blah, 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 blah. Okay, so then if I create a matrix whose columns are orthogonal vectors, and I did Q transpose times Q, Q transpose times Q is kind of like Q transpose times each of the columns of Q. What is Q transpose times like U1 then? It's all the dot products. of like U1 with these three. Which and then if I made them all unit vectors, then dot product of U1 with itself would be 1. And then U1, this dot product would be 0, that product would be 0, so I get 1, 0, 0 for the first column. And I get 0, 0, 0, 1, 0 for the second column. And so I get the identity matrix. Okay? And to make unit vectors, you just divide by the. So then we have a special set. So an orthonormal set is orthogonal vectors that are each unit vectors. Okay? So an orthonormal set is the thing that's most like our I, J, K, our E1, E2, E3 set of vectors. Okay? And so then here's an example of an orthonormal set. U1 is this, U2 is this. Okay? So then you could create like Q could be like put them in as columns, and then Q transpose Q is just gonna be like boom, the identity. Okay? So then doing Q transpose Q gives me identity is not a very like useful thing. It's the other way that becomes useful. Okay? So do you remember Calc 3 doing projections? How many different things you'd have to do in your calculator to get the projection right? You can do a whole bunch of projections at once using matrix multiplication. Okay? So basically say I've got B, projecting B onto W, I'm going to call that B hat. And the vector orthogonal to that is B minus B hat. And so then that has a Pythagorean theorem. And so we get the Pythagorean theorem there. And so then basically the orthogonal projection of B onto W is the vector B hat in W that's closest to B. Okay? And so then and you can find B hat using just like B hat's just projection formula, right? But then the projection formula is just like that. And so the projection formula is just like that. But then that's really like, if they're unit vectors, then these are all ones, right? So if I had unit vectors instead of W's, it would just be this, right? And so then if Q was this matrix, then this thing is really like Q transpose B. So projecting B onto a subspace, not even just one vector like we did in Calc 3, but projecting onto a subspace, if you have an orthonormal basis of that subspace, you just do this, and you project it on. Okay? And this is how, in statistics, you find the function that fits your data. Okay? In statistics, when you're finding a function that fits your data, you're basically just doing this. Okay? All right. So I think we'll leave that there because we'll leave that there. And then the next section was how to create an orthonormal basis, and then which is this cool thing called the Graham-Schmidt process, and then orthogonal least squares is the idea of like finding the line that fits the data. And so then you can do that with, like, you normally in stats you only do it with straight lines, but once you're doing this linear algebra stuff, you can do it with any function. Okay? Straight lines are just nicest when you don't know linear algebra. When you know linear algebra, this all becomes easier and you can do any of this. Okay? All right. I'm going to pause there, though. We're going to take a 5-minute break, then we're going to study for the final exam. Okay?